So an example, though, of what we can use this now, so let's do an example problem, is what force, full vector notation, force do you feel, feel halfway between the sun and the earth? If you're just parked there in space and you're weightless, what force would you feel? Why the circular one is negative? They're both negative because it's attractive. It's pulling in the negative r hat direction. I kind of bumbled it at first, but you put m1 at the origin, and then m2 gets pulled towards it. R hat is defined, the unit vector of r hat is defined as outward. It's a positive vector, magnitude 1, pointing away from the origin. Gravitational pull towards the origin. So that's why the negative's there. Yeah. Okay, so here we go. Let's use this stuff and see if we can figure it out. Just for one simple, like 1D problem. So here's the sun here. I always put sunglasses on my sun like that. And then the sun is here, and the earth is here. I'll label the earth. I mean, the sun is like, you know that's the sun. Is the r vector always pointing in the direction of the point mass? It depends if you mean r hat vector. Let's just not worry about the r hat stuff. It was just enrichment. Okay. But if you want to talk about it in office hours, we can talk about it for hours. I'll teach you all of vector calculus in I could do it in 8 hours. If you want. Okay, so say you're halfway between the sun and the earth. Oop, there you are. What force do you feel? I just want more practice calculating these forces. Here we go. So you need a bunch of astronomical quantities to do things like this. And they all work out that they're just right. Maybe God isn't malevolent. Maybe he or she is actually, what's the opposite of malevolent? Benevolent, too slow, okay. 2 times 10 to the 30 kilograms, and the mass is 6 times 10 to the 24 kilograms. So because big G is so small, big G is small, it takes big numbers to do anything interesting. So the separation between the sun and the earth is 150 billion meters. And then you say, is that from the center or the surface? And that so far doesn't matter. Okay, so the size of the sun is kind of like 0.1% of that. So if the difference is negligible, then it doesn't matter for our calculation. So what we want to do, though, is this is a vector calculation. We have 2 gravitational forces, right? I weigh 70 kilograms, sort of. And what we want to do is say, well, let's draw a free body diagram. Here we go. Well, mg down. No, we're not on the Earth anymore. Mg's not down. Okay. So now we feel a general universal gravitational force towards the Earth. I'll call that Fe. We're attracted to the Earth, right? 2 bodies, everything's attracted. F sun, this way. Now, did I write unit vectors and all that stuff? No. For what we're going to do, you can pretty much do just sort of the polar coordinate system and do it visually. You know this is attractive because it's this way. You know this is attractive because it's that way. You want to get into it? Okay, this is the origin. Which way is r hat? R hat, when you're here, when you're looking this way, r would be defined as this vector to here. R hat that way is this way. That's why the force, oh no, you got to put it at the origin of the Earth. I'm just going to stop saying that. Okay. The origin has to be here, r hat is that way, the force is that way. But anyway, you won't do r hat. You're just going to look at the forces like this. Attractive, right? So now we just calculate it. We just say, okay, then the force, the total force is the force the Earth on you, right? Earth on you and the sun on you. Force of the Earth on you plus the force of the sun on you. So it's 2 vector forces and they add. Okay. Here we go. So we write them down, and you could do it in a Cartesian coordinate system. You just got to realize that they're the opposite direction, right? So you got to pick which way you're going to define as positive. Let's say that's the positive direction, positive x. So what you will do is just manually say, I know that the force of the Earth on me is in this direction, and I know the force of the sun on me is this direction. You just do that manually. And you say, okay, the sun on me is g, mass of the sun, times 70 kilograms over half of this separation squared, right? 75 billion times 10 to the 9 meters squared. And that one, I'm saying the sun was negative, so I'm going to put the negative sign in. So we're just doing it manually. This one is in the positive direction because I'm on the left side of the Earth on this coordinate system. So plus g, and then I'll put the mass of the Earth in there, minus 70 kilograms. And then again, since I put halfway, it's 75 billion meters, right? 75 times 10 to the 9 squared. Okay. And then you could look at that and say, well, I mean, most of these terms are the same, right? You've got the G, you've got my mass, 70 kilograms, you've got 75 billion meters. Those terms are all the same. The only difference is the mass of the sun and the mass of the earth. Okay, so we could just write those down. We could just add those two because we're looking to see something cancel. Let's see. We're looking to see these two things cancel. So what we have is negative mass of the sun plus the mass of the earth. So it's nothing's going to cancel, but let's look at the sizes of these things. Right? So now we look at this and say it just is proportional to these masses. This one is 6 times 10 to the 24. This one's 2 times 10 to the 30. So this is like 1/millionth of this. Right? The force that the earth is applying is 1/millionth the force of the sun. Because we're halfway in between, right? If you're on the surface of the earth, then you're so much closer that its force becomes bigger. But if you have the same distance and the same g and you have the same mass, all it depends on is the mass of the sun and the earth. And the sun is much, much bigger. 1,000,000 times more massive. So this, you can basically just say that's like 0. We'll just ignore that. If you want to put it in your calculator, you can basically subtract or take negative this plus that, and you're basically going to get negative this, right? Because it's 1,000,000 times bigger. So let me just finish it, and then we'll answer all the questions. So then you do all this, and what do you get? This was the plus x direction. You get a negative number, and you get negative 5 newtons. I just thought it was funny that it came out to something so simple. Negative 5 newtons if you're halfway between the sun and the earth. Why negative? Because it's this way. Because I defined positive x that way. Did I do this with some detailed setup Cartesian system where I had a general expression that's always true in this Cartesian system? No. Because that's impossible. You can't do that. I just said, I'm defining this way positive, therefore I know the sun's force is negative because it's attracted to the sun. I'm defining this one positive because I know it's attracted to the earth. We did the signs manually because we have to. Right? Okay, now we're about R vectors. Is there any reason to use the sun's mass for the Phi, the F-E-Y? This is the, oh, okay, flip them over, sorry. There's no rule that says I have to maintain the spacing going down the board. I mean, that would be not being a jerk, but you know, there's no it's not in the student code or anything. Why is the mass of the earth written as 0? Because it's so small. Get out your calculator and put 2 times 10 to the 30 and then say minus 6 times 10 to the 24 and see what you get. You're going to get 2 times 10 to the 30. You're subtracting two numbers, and one is 1,000,000 and one is 1. So in physics, we just drop the 1. It doesn't make a difference. You can keep it. But the reason we do that is when we're doing things symbolically and we're trying to get a simple formula that makes everybody happy, if you leave all those teeny numbers in, it makes a giant mess. It doesn't make us happy. So that's how we do it. Numerically, you don't really have to drop it. But we're learning that because you want to be a physicist someday. Why is the force 2 acting on 1 negative? Oh, I don't know. I've given up. Let's move on. It's always attractive. It's always attractive. I put the origin in the wrong place, and that caused confusion. Sorry.